Hello, students. Our next lecture is going to be on Markov chains. This is our next topic in Math 418. And what this topic is actually something we've already seen. So, Markov chains are just a special type of state diagram. So, in the same way that if you remember a compartmental diagram, a state diagram was a type of compartmental diagram, right, where we made the restriction that you could only have arrows going between states. You couldn't have anything coming in from the outside, right? So that was a state diagram was more specific than a compartmental diagram. A Markov chain is a special type of state diagram now, okay? And so what a Markov chain is, and I've got one drawn up on the board here, you'll see it looks just like a regular state diagram, but a Markov chain has one additional condition that a state diagram didn't necessarily have to follow, and that's that all of the arrows out of a state have to add up to 1. Okay? So okay? So if you look at this state diagram that I've got up here, if you look at the arrows coming out of x1, so coming out of x1, we've got 3 arrows. So this one, and this one, right? And so 0.6, 0.3, and 0.1 are the weights on those arrows, and so 0.6 plus 0.1 plus 0.3 adds up to 1. Similarly, the arrows coming out of x sub 2, 0.5, 0.2, and 0.3 add up to 1. The arrows coming out of x sub 3, 0.2, 0.1, and 0.7 add up to 1. Okay? So notice that this is just a condition on the arrows out. The arrows in don't necessarily add up to 1. So like, for example, if you look at the arrows into x1, we've got 0.2, 0.3, and 0.7. That adds up to 1.2. Okay? So it's just the arrows out that sum up to 1. Okay? Why is this the case? Why are we interested in Markov chains? So a Markov chain, in this case, this represents a situation where the number of objects isn't changing. So if you think about it, if all of the weights out add up to 1, so like 60% of what's in state 1 ends up in state 2, 10% ends up in state 3, 3% or 30% ends up in x1, the number of total objects isn't going to change. Okay? And so Markov chains are used when we have a situation where we don't have anything changing as far as the overall number. So unlike our state diagrams where we saw, like for example, it might increase at an exponential rate or decrease at an exponential rate, the total number is not changing in this situation at all. And so you saw this on homework 3. One of the final problems was a state diagram where the eigenvalue was 1 and it stabilized. Okay, so a Markov chain has the quality that all of the eigenvalues are 1, not just the dominant eigenvalue, and so the total amount never changes. Okay, it stays fixed. Okay, so you can think about these weights as representing probabilities. So you've got this fixed number of objects, and there's a certain probability that we move from one state to another. Okay? So that's, again, if you think about probabilities, we know that probabilities, remember, all of the probabilities have to add up to 1, right? So that's a kind of a way of thinking about Markov chains. Okay? Now, Markov chains work in very much the same way that state diagrams do. This is a state diagram, right? So everything you can do with a state diagram, you can do with a Markov chain, okay? So you could look at the eigenvalue, you could look at the dominant eigenvector. The dominant eigenvalue, of course, will be 1. The dominant eigenvector will be the percentage that end up in each category. In the same way that it was for state diagrams. So all of that still holds. What we're going to see is that Markov chains have some additional structure because they have additional properties, right? And that's our general rule overall with mathematics. If you add additional structure, then you're going to get additional properties that you can use. Okay? So just like we would do with a state diagram, we can figure out what the equation is from this. So if you write this down, x sub n, we get a matrix equation. So if you look, x sub 1 is 0.3 x sub 1 plus 0.2 x sub 2 plus 0.7 x sub 3. X sub 2 is 0.6 times x sub 1, 0.5 times x sub 2, and 0.2 times x sub 3. And then x sub 3 is 0.1 times x sub 1, 0.3 times x sub 2, and 0.1 times x sub 3. Right, so we get a matrix equation just like we would with a state diagram. And you can see here, notice that the columns of this matrix, 0.3 plus 0.6 plus 0.1, 0.2, 0.5, 0.3, 0.7, 0.2, 0.1, all add up to 1, right? And that's because the columns are the arrows going out of a particular state, right? So these are all the arrows going out of 1, out of 2, out of 3. And so those add up for the same just because of that Markov chain property. So you can think of this Markov chain property also as being all the columns in the matrix add up to 1. Notice that the rows don't necessarily, right? Again, because those are the arrows going into a particular state, not out. Okay? So let's see. Okay. So one other thing with a Markov chain, as far as how we think about these, and then I'm going to end this, and then I'll start another video to talk about kind of some of the properties of these Markov diagrams and the things that we do with them. So what we're going to do is we're generally, when we're building a model here, we're going to think about the values in each state as being percentages, okay? So for example, if you say you were building a Markov chain to look at electoral districts in the United States, right? So electoral districts in the United States are fixed. The number of representatives that are elected is 435, I think, right? And so that's a fixed number. And so you might build a Markov chain where you say, okay, this percentage are Republican. That would be your state 1. This percentage are Democratic. That would be your state 2. This percentage are independent. That would be your state 3, right? And so you might start with, for example, 60% are Democratic, 43%, or that adds up to more than 100. 60% are Democratic, 35% are Republican, and 5% are independent, right? And so you would have some sort of like 0.6, 0.35, 0.05 would be your state. Those values represent the percentages of the overall amount rather than numbers, right? So rather than using for your values, say there are 157 districts that are Democratic and 125 that are Republican, something like that, you can just use these percentages, okay? You could use the numbers, right? It would get you the same kind of result. Everything would just be multiplied by 435. But what we generally do as a convention with Markov chains is we use probabilities. And you'll see that in the example that we do next, kind of that we think about them as being probabilities, percentages of the total rather than the actual numbers, just because it makes the numbers look a little bit nicer. Okay? In the next lecture, we'll go over some of the properties and talk about this particular example, and then we'll do some real-world examples to see how this works.